Hey everybody, Dr. A here, and in this video we're going to be exploring a virtual work example in order to calculate a beam deflection. So let's go ahead and get started. In the given information, we're being asked to use virtual work to compute the vertical deflection of point B. We're being told that the beam is made of a material with a modulus of elasticity of 29,000 ksi and a moment of inertia about the bending axis of 144 inches to the fourth. We're then being asked to confirm our solution using the appropriate pre-derived formula. So the beam we're given is a cantilever beam. We have this fixed connection at A and it's free at B. The cantilever beam is subject to a uniformly distributed load over its entire 10-foot length, and that has a magnitude of 0.3 KLF, which is kips per linear foot. Now, before we dive into this, it would be wise for us to get our units consistent. Remember, you always have to have consistent units. So if you notice, our modulus of elasticity is in terms of kips per square inch, and the moment of inertia is in terms of inches to the fourth. But here we have 0.3 kips per foot. So we're going to convert this kips per foot to kips per linear inch. And we're going to do that by dividing by 12, okay? So if we divide by 12, we'll get that this is 0.025 kips per linear inch, KLI. And we again do that by saying 0.3 KLF times 1 foot over 12 inches. So that gets us kips per linear inch instead of kips per linear foot. Now we have consistent units with our E value and our I value. So let's go ahead and dive into this using virtual work. Well, what do we do in virtual work? Well, the first thing we're going to do is establish a virtual beam, okay? So I'm going to go ahead and draw this out. I'm going to say that we have a virtual beam, or you can maybe call it even a virtual system. And I'm going to sketch that fixed connection here. I've got the beam length here, and I'm going to put a unit load at the point of interest in the expected direction of deflection, okay? And this is going to be 1 kip, all right? Now, this virtual beam is still 10 feet long, okay? So I can go ahead and, put that dimension line here. 10 feet long. Now, I also need an x coordinate. Remember, we need to define the domain here. Now, we have some options on defining the domain. We could call the fixed connection the origin and call x positive pointing to the right, or we can call the free in the origin and point x positive to the left. I'm going to do that second option just so I can avoid having to determine external support reaction. So I'm going to call that positive x, okay? Then what I'm going to do is use method of sections to compute my virtual moments, my little m moment, okay? So in order to do that, here's what I'm going to do. I'm going to use method of sections. I'm going to say MOS free body diagram. I'm going to make a cut. And what am I cutting? I'm cutting at a distance of x, okay? So this is a distance x that I'm cutting here from that free end. Here's that 1 kip. And what's going to become visible at this cut? Well, of course, I'm going to have an internal moment, little m, that I'm interested in. Do I have a shear force here? Yeah, technically I do. I also have a shear force here as well, but I'm not really interested in that shear force. I'm just interested in that little m moment, okay? So here I'm going to say sum of the moments about the cut equals 0. And at this stage, this is just a method of sections, okay? So I'm going to say negative little m, and then I'm going to say also negative 1 kip times x equals 0. So little m is going to be equal to just negative x, okay? And so that's my internal little m or virtual function. And of course, this is going to carry units collectively of what? Of something like kip feet or maybe even kip inches eventually, okay? Now, what do I do next? I'm going to draw the real beam again, okay? I'm going to draw the real beam. So I'm going to come here, I'm going to say real beam, and I'm going to analyze that one. So I've got that same fixed connection. I've got this uniform load, and the real beam has this real load on it. And we said this was 0.025 kips per linear inch because we want to have consistent units, okay? Now, what is the length of this beam, okay? What is the length of this? So this is 10 feet, but remember, we need consistent units. So, and the length units matter even more now because I've got this distributed load that's got a per inch there. So I need to write this not as 10 feet, but as what? 120 inches, okay? Now, I also need to use the same location variable x that I did in my virtual beam, okay? I need to have this same location variable x here, all right? And I'm going to do another method of sections, free body diagram, MOSFBD, all right? And I'm going to make that cut section. And here I've got this uniform load, okay? So I've got this uniform load spread out here. That's the 0.025 KLI. And what is this cut length? Again, this is a distance of x, all right? This is distance x. And then I've got this capital real moment, M, showing up here. I also have a shear force here as well. But remember, we're not interested in shear force. We're just interested in the moment here. So now I'm going to say sum of the moments about the cut equals 0. I'm going to do that again. And of course, I'm going to have minus capital M. And then I'm also going to have minus 0.025 KLI. There was a KLI there. I think I had a little typo there. Made such a big deal and telling you to be careful about that. KLI. Use consistent KLI there. Okay. So 0.025 KLI, and then times what? Times x, and then times an x over 2 equals 0. Do some rearranging. Capital M equals negative what? Well, we just can lump those constants together. 0.0125 x squared. And that's going to carry units of, collectively kip inches. Now, what did I say earlier when we were setting up our virtual moment? I said collectively this has units of kip feet. Well, I mean, it's kip feet or kip inches. I mean, you can just as easily call this kip inches in this virtual moment. The reason why it's less critical in this virtual moment is because this is a single point load. So you're cutting at a distance x. It could be kip feet or kip inches. It's kind of irrelevant here because you just have that single point load, okay? Where it becomes very relevant is when you have a uniform load or some kind of distributed load where you have a per linear inch or per linear foot. That's when you got to be a lot more careful with what you're doing, okay? So am I done? Well, I've done a lot of the work here. I now apply my virtual work formula, okay? What does the virtual work formula say? Well, it says you say 1 kip times delta B, all right? And then we're going to have the summation as I goes from 1 to n of what? The integral from 0 to L, little m, capital M, over EI dx sub I. But we only have one domain, right? We only had the 1x coordinate system that was established. And so the summation doesn't really come into play. I just have one term, right? So I'm going to have 1 kip times delta B equals the integral from 0, and L is 10 feet, but really it's 120 inches. Remember, consistent units. And then I'm going to have negative x for my little m, and then minus 0.0125 x squared for my capital M, all divided by EI dx, okay? And remember, EI is a constant, so you can pull that out, and we have those numbers of EI that we can substitute in here in a minute. So I'm going to show a little bit of work here. 1 kip delta B. You can put this integral into a calculator, although it is an easy integral to punch in. I'm going to go ahead and put that in my TI-36X Pro. So I have 0.0125 times x, and it's really times x cubed now because I lumped it all together. So let me do that. 0 to 120 inches, and then 0.0125 times x cubed. And so we get this big number, okay? We get this 648, 000, all divided by EI. Now, I want you to be careful. That numerator, this 648,000, it does have units, okay? What are those units representing? Well, with consistent units, what should this be? You have a moment in kip inches times another moment, which is also times kip inches. So you have kip squared, inches squared, and then you have a dx here that pops out through this 120 inches. So really, that numerator carries units of kip squared times inches to the 3rd power, okay? Now let's go ahead and substitute in EI, all right? So if I put equals here, let me change the colors back, put equals here, 648,000 kip squared times inches cubed. And remember that numerator collectively has the units of kip squared inches cubed, divided by 29,000 kips per square inch. That's what a KSI is, times 144 inches to the 4th, okay? So let's punch that through and see what happens. We divide by 29,000, then we divide it by 144. So I get 1 kip times delta B equals 0.1552. Now, what are my units here? Well, some kips end up canceling, okay? So I can say the kips down here cancel with one of the kips in the numerator, and then I have inches squared canceling with inches to the 4th, leaving inches squared in the denominator, and then I have 2 of those inches squared canceling with 2 in that numerator. So right now, this 0.1552 is going to carry units of what? It should be kips times inches, which makes sense. This is an energy method, and this is a type of energy. Now, the kips are going to cancel with the kips on the left hand of the equation, and what am I going to end up with? I'm going to get delta B equals 0.1552 inches, and that's going to be a downward deflection. How do I know it's downward? Well, remember from virtual work, if the value comes out to be positive, which our value did at the end of all the calculations, then that means that this deflection is in the direction that we put the virtual load. So back here, we put the virtual load pointing down. We did the calculations. The final value came out positive. So delta B is, in fact, pointing down. Now, the last part of the problem asks us to check with a pre-derived formula. So let's do that really quickly. I'm going to change colors here. I'm going to say pre-derived formula, and these formulas are found in pretty much any structural analysis or mechanics of materials textbook. So the pre-derived formula for this particular loading case would be WL to the fourth over 8EI. Okay, and so and that would be, these may show up with a negative, which means it's pointing downwards, but pointing up or down is going to be indicated by W basically. So we substitute these values in 0.0125. 0.025 KLI times 120 inches to the fourth power divided by 8 times 29,000 kips per square inch times 144 inches to the fourth. So let's see how these units kind of combined. You have some kips, and kips end up canceling. Inches squared end up canceling with two of these. And then you've got the per inch canceling with one of these and giving you inches cubed, and then inches squared cancels with two of these, leaving you with inches finally. And so you should get, if I punch this in my calculator, 0.025 times 120 raised to the fourth power divided by 8 divided by 29,000 divided by 144, and sure enough, I get exactly the same thing, 0.01552 inches downward. I suggest you pause the video, rewind it, make sure you understand this unit management and how all of this packages together. But this is our final answer, and that concludes this video. Please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.